Good morning. All right, so today we're going to look at applications of exponential functions. And exponential functions show up in the real world in a lot of ways. And here's the basic function that we're going to use is kind of a parent function for our examples. Okay, so we're going to use this model p of t, so that's my function name, capital P of t, equals p sub 0, a to the kt power. Now, what on earth does that mean? And actually, we'll just say to the t power. So let me explain what we're talking about here. So here, we're modeling some sort of, we'll have two applications. All right, one is we're going to have population growth. All right, so that's one way we can model that. One application of exponential functions is through population growth, and that means population of a community, population of a bacteria culture. We can measure this with the spread of a virus, those kind of things. You may have heard with the spread of COVID that we're talking about flattening the curve, or a lot of times you hear about exponential growth, and the exponential growth comes from these applications, all right? So t, usually my variable, represents time. This a is my base, and that's determined by how quickly it's growing. And this p sub 0 is the initial population. Okay, and so the idea is, if you started with a larger city, you're going to grow at a faster rate. So this initial population, that's where that comes into play. Another application of this we'll see later on is not only could you have growth, but you could also have decay. All right, so here we have decay is another application. So we'll say or decay is another application of these type of functions. We'll look at both of them. And even though that seems like completely opposite ideas, right, they actually go hand in hand. All right, so let me show you the first example, kind of see what we're talking about, and it's not really a huge deal, okay? So you got to let me write this down because we're dealing with an application here. All right, so here's what we're starting out with. So we have a biologist is growing bacteria in a petri dish. We'll say cultivating bacteria. All right, and here's the details. She starts with 1,000 bacteria. She starts with 1,000 bacteria. And she's going to give it enough food so that for the first 5 hours, it grows exponentially, doubling every hour. Okay? We'll say with enough food source that the population doubles every 5 hours. Doubles every hour for the first 5 hours. And so one thing you have to kind of know is these exponential curves. We learned in the last section that the graphs of these things just take off like this. They just skyrocket. So in realistic situations, that's not going to last forever. After a little bit, it's got to level out somewhere. So when we talk about exponential growth, we're talking about for a short time, it's exponential growth. So in here, for the biologist with the bacteria, it's the first 5 hours, and I left out 5 there. In a population setting, it might be for like the first 10 years or something like that. So the first 5 hours. Okay, now what we actually want to do is, first of all, we want to figure out what kind of function models this situation. All right, so let's call it the growth function. All right, now what we know already about this growth function is that it looks like this p of t thing that we had earlier. So p of t equals p naught a to the t power. And what we know is that p naught is 1,000, right? Because it said that she started out with 1,000 bacteria. We also know that it's going to double every hour. Okay, so since it doubles every hour, since the population doubles, I know that at time t equals 1 hour, I mean, if you start out with 1,000 and then 1 hour later you've doubled, how much do you have? You have 2,000, right? I know that p of 1 is going to be 2,000. So that's going to allow me to figure out what the value a should be, right? Because now what I know is that 2,000, which again is p of 1, equals 1,000 a to the first power, okay? And so now I can divide both sides by 1,000 and end up with 2 equals a to the first power, or just a equals 2. So my model then, that models the situation, is 1,000 times 2 to the t power. Okay, does that make sense? And here we're measuring t in hours, and our model, we think our model is going to hold for the first 5 hours, right? Okay, does that make sense? I hope it does. All right, let's look at another application, or what we can further do here. We want to know how long it's going to take. So how long until we reach, how much do we want? 16,000 bacteria. Okay, so now we know our function. How long is it going to take to hit 16,000? All right, so what we're trying to solve then is this equation. So we solve 16,000 equals 1,000 times 2 to the t power. All right, so I'm going to divide both sides by 1,000. I'm going to isolate 2 to the t power. So I divide both sides by 1,000. I get 16 equals 2 to the t power. Okay, now this is what we covered in the last section, but all we have to do is figure out, can I write 16 as 2 to some power? And I can, right? This is the same thing as 2 to the fourth, right? If you don't remember, 2 times 2 is 4, and then you multiply that by 2, you get 8. And that's not a good way of writing this. Okay, let's see. 2 to the first is 2, 2 squared is 4, 2 cubed is 8. 2 to the fourth then is multiplying 8 by 2, you get 16. All right, so 2 to the fourth is 16. And so now look, 2 to the fourth equals 2 to the t. The conclusion then is t equals 4 hours. And there's my answer. It's going to take 4 hours to get 16,000 bacteria. Again, all I had to do was divide both sides by 1,000 to get the 2 to the t by itself, and then hopefully write 16 as 2 to some power, which we could do. And we write it as 2 to the fourth, and so 4 is what t is. All right, now the other thing we want to know is how much do we have after 2.5 hours? So how much bacteria after t equals 2.5 hours? All right, so this is just a matter of plugging in the value 2.5 in for t, right? Because didn't we say t measures the number of bacteria in hours? So I'm going to say 1,000 times 2 raised to the 2.5 power. Okay, now this is a calculator thing, right? 2 to the 2.5 power is not something I know off the top of my head. Maybe we could work it out, but we don't really need to. We're just going to use a calculator, and you should get around 5,657 bacteria. Okay, you're going to get a decimal, but you can just round that up. All right, and I hope that makes sense. And again, the way I found that was a calculator. And I haven't really said that you need a calculator much in this course. The truth is you don't most of the time. Here we are going to need a calculator. All right, I hope this makes sense. Population growth. Now this is bacteria, but we could easily change this to a virus or a tortoise population, the population of a city. You need to take a class called differential equations. And this is kind of the basic application that we get out of a differential equations course. Okay, now the other thing we could look at in terms of an application is decay. I mentioned that. All right, so let's label this one growth. This first example is growth. Now let's look at a decay situation. All right, now the way with decay, you get the same function, we'll call it a, like that. a sub 0. So it's the exact same model, okay? The only difference here is that a, my base, is between 0 and 1. And we didn't mention this with growth, but with growth, you want your a to be bigger than 1. Okay, so that way when you multiply a by itself over and over, it's growing. If you have a fraction between 0 and 1, you keep multiplying it by itself, it's actually going down. Okay, it's getting smaller. We saw that in the last section, that the graph looks something like this. Okay, so it's going to go down as time progresses. All right, now where you see this in the real world, I mean, where do you hear about decay? Some sort of biological decay, which could work. Here, though, we're looking at typically with chemistry. So you've heard of carbon dating. The way carbon dating works is that we understand in a natural setting how long it takes for carbon to decay. So you can find a fossil, measure how much carbon is left in that fossil, and that should kind of, if you think retroactively, kind of help you figure out how long it took to decay to get to its current state. And that's the idea. Now, carbon dating is not foolproof because we've seen that some natural disasters and things like that can accelerate the decay of carbon, or maybe we have a bad sample, but it does give us a good estimate, and the mathematics does hold. So we see this, another application. Well, let's look at the example we have here, and then I'll give you another application I saw that's an interesting example of radioactive decay. All right, so here we want to look at the decay of carbon-14 in years. All right, now what we know here is that carbon-14 has what we call a half-life of 5,728 years. Now, what on earth does that mean, a half-life? The half-life is the amount of time it takes for an amount of carbon-14, or amount of anything, to decay to half of what it was. Okay, so half-life is the amount of time, let's say the time it takes for a substance to decay to half of its original quantity. All right, so with carbon-14, what we're saying is you have 1 kilogram of carbon-14, and then after 5,728 years, you now have 1/2 kilogram of carbon-14. All right, so after 5,728 years, your 1 kilogram is now half a kilogram. And that's the idea behind this. And so based off this, what they're asking us to do is find, I didn't really write it out very well, did I? Find the model for the decay of carbon-14 in years. So we know its half-life. Based off its half-life, can we figure out a way, the actual function, this a sub t function for carbon-14? Okay, so what we know here is that it doesn't really matter how much we start with, okay? So we can just start with, so let's let a sub 0 just represent the initial amount. Be initial amount, and that is, you know, when you plug in 0 in for t. This is how much we started out with. Okay, so what we know then is that so when I plug in my time 5,728 years, we went from what I initially started out with to half of that, right? So I ended up with a sub 0 divided by 2. Okay, now from that we can figure out what our value of a is, because what we also know based off our model, so we're using here, remember, we're using the a sub t equals a sub 0 a to the t power, right? So when I plug in t there, and I apply this model, I know that that's a sub 0, a to the t power, in this case, t is 5,728. So I end up with the equation then that a sub 0 over 2 is a sub 0 times a 5,728. Okay, now I can divide both sides by a sub 0 and end up with 1/2 equals a to this power. All right, and that means then that, how do you do that? How do you solve that? Well, think about if I had like this, a cubed equals 8. What do? You say you take the cube root of both sides to get 2. Another way of saying that is you could say that's 8 to the 1/3 power. Remember, these fraction exponents mean the roots. So if I'm trying to solve for a, I need to take 1/2 to the 1 over 5,728 power, or the 5,728th root of 1/2, which is something we'd want to plug into a calculator, right? Obviously. And so you can plug in 1/2 to that power, and you should get about 0.999879. Okay, so how quickly does carbon decay? All right, my function then for carbon. So for carbon 14, our function is a sub t equals whatever your initial amount is, okay, times 0.999879 to the t power. And that is your function. That's how quickly we're decaying. And I hope that makes sense. So if you had a sub naught, maybe you found a 100 kilogram sample, right? And you could tell based off, maybe you know something about the bone density of this particular creature, then you can figure out how much had decayed already and retroactively figure out about how old that sample is. And that's how carbon 14 or carbon dating works. We can do this with a lot of things. This is also how we know like how long a nuclear reactor is going to last, that kind of stuff. All right, now I hope that makes sense. Okay, so we're going to turn to another example that, and I think both of these examples are have been pretty useful over the course of human history. I mean, surely exponential growth, we're seeing how that is helping us as a society today. Decay has helped us kind of understand the world a little bit better. I was going to give you an example of decay. An example that I saw one time that was interesting is that when you post a link, let's say you do some sort of social media post, like an Instagram post, and you're wanting to, from that moment in minutes, count the number of interactions you get. Maybe for Instagram, the number of little hearts you get, okay? So that happens with radioactive decay. After so many hours, you've already reached the half-life of that link, or of that picture. So that means then let's suppose the half-life is 3 hours. So within the first 3 hours, you're now going to get half of the hearts that picture is going to get for all eternity. So for the next 100 years, you're going to get less than half of the total number of likes, which is kind of weird that those things work that way, but it also shows you how quick of a rebound or how short-term memory we have when it comes to social media, right? All right, so let's look at another example of something that's going to affect your life a lot, and that's with this idea of called compound interest. Now, the way compound interest works, let me set up a table. So let's say you have an initial investment. We use A. We're going to let P be our principal. Principal here is what you invest, okay? And we're going to have these are my periods. So that could be months or years or something. And the way compound interest works is you accumulate interest not on just the initial investment, but what is there already, okay? So for example, and this is the way it works, on the first period, what you have now, your future value, is going to be the principal times 1 plus this thing r over n. Okay, now the r is the interest rate. So for example, if you have a home mortgage, you might get like a 3.5 interest rate. The n is the number of compounds in a year. All right, and we'll explain more what that means later. And what I'm trying to explain here is how quickly, when you think about interest this way, how quickly it grows. Okay, it's going to grow faster. So for example, I said 3.5%. Interest is actually growing faster than that. Okay, so for the second one, for the second period, I have the initial investment plus that interest from the last month, and that would be how you calculate simple interest, but we're actually going to now add on more interest. We're going to multiply this by another interest compound. Okay, so that's going to be 1 plus r over n squared. And as I keep doing this, so let's go down to the kth period. My interest is going to be the principal times 1 plus r over n times 1 plus r over n plus 1 times r over n, blah, 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 k times. We get 1 plus r over n to the kth power. And that's how you calculate how much interest you have. Now, where does this affect you? If you have taken any sort of loan, if you have a car payment, if you have a mortgage, if you have a credit card, or if you have a savings account, all of these things are being affected by compound interest. Eventually, when you start investing for retirement in a mutual fund or a Roth IRA or something like that, all of these things work upon compound interest. And this is when they say let your money work for you. That's what they're talking about. If I can just invest a certain amount and just let it sit there over time, it's going to grow. And it's going to grow with this exponential growth of compound interest. Let me give you an example. And these are sometimes surprising. So this is example 3 in your textbook. Sandy invests $10,000. Okay, so investing $10,000 at 4.5% interest, and it's compounding quarterly. All right, so this account is applying the interest quarterly. So that means 4 times a year, or once every 3 months. So what we want to know is after 3.5 years, what is her value? Okay, so what is the account value? The financial term for that is future value. After t equals, let's say 3.5 years. All right, so all we're doing here is applying this formula, a sub t, the future value, a represents future value here, p, which is my initial investment, times r over n to the k power, okay? And here k gets replaced with the number of times we compound it times the number of years it's been invested. Okay, so this is the model that we actually use. Okay, and maybe I should write this out here. We're going to use a sub t is your principal times 1 plus r over n to the nt power. All right, so now watch how this works. If you've never seen this before, this is something you definitely need to look into. All right, so my initial investment was $10,000. The annual interest rate is the 4.5%, so it's 0.045. N is the number of compounds in a period. So compounding quarterly, we have 4 compounds, and 4t. So that's my a sub t power. Now, what am I plugging in? T, remember, is years. I want 3.5 years, so we want to figure out a of 3.5. So that's going to be this 10,000 1 plus 0.045 divided by 4 to the 4 times 3.5 power. All right, now this is a calculator thing. You want to practice calculating this because it's very easy to get some sort of syntax error, just not putting it in correctly. But this should grow to $11,695.52. Okay, so you have someone in your family that's telling you to put your money in a mattress. Well, you put your money in the mattress, you put $10,000 in a mattress. After 3.5 years, you have $10,000. Now, with the rate of inflation, that may not even be worth what it was when you first put it in. But if you put it in an account, you started out with $10,000, you didn't touch it, right? You now have $11,695. So you gained $1,700 just by letting it sit there. That's what making your money work for you means. Okay, great. Now, let me show you something interesting that happens with this. So, compounding quarterly, usually you don't see that on an account. Okay, so typically an account doesn't compound quarterly, compounds monthly. Okay, so like a mortgage might compound monthly, or what's even worse is daily. So some credit cards compound daily. All right, now the thing is, the more compounds, the quicker the compound. Oh, let me say this. I think it's better to say the more compounds in a year, the faster the interest grows. Okay, so the book has an example. Let me do this table. It's pretty neat. So here we're going to have n, and here's where we're going to have value after 1 year. Okay, so here we're going to have 1, that's an annual compound. Let's do biannual, quarterly, monthly. Let's do weekly, daily, and then hourly. So that would be 8,760 compounds in a year. All right, and here's what we're going to do. We're going to invest $1,000 with a 5% interest rate. So if I only compound it once, and here we're compounding after 1 year, so we're letting, so in this case, n is 1, t is 1. And if you do that, so compounding annually, you got $50. I mean, that's not bad, right? Okay, so if I do it twice a year, I get 1,000, 1 plus 0.05 over 2, all right, to the 2 times 1 power. And you're going to end up with not a lot more. You get an extra 63 cents, okay? So if we're filling this out, we have 1 plus 0.05 over 4 to the fourth, and 1,000 times 1 plus 0.05 over 12 raised to the 12th power, and so on. So we're dividing by 52 raised to the 52nd power. I've made it this far, I might as well go ahead and write them all down, right? So here I'm dividing by 365, raising it to 365 power. And then lastly, if I do it hourly, what we're trying to see here is how much does this get affected? And it's not exactly obvious. I mean, look, each time you're dividing by a larger number, so the amount of interest per compound has gone down a lot, but you're also adding a lot more compounds. So how quickly is that growing? So going from 1 to 2, you only gain 63 cents. If you go from 1 to 4, you only gain 95 cents. So it's not a big deal. And even monthly, you gain an extra. You gave $51.16. Okay. If I do weekly, you get $51.25. And then the daily and the hourly are going to barely even be noticeable. It's going to be less than a penny difference between those, okay? But the point is, notice that as the compounds go up, the value goes up as well, right? So as the number of compounds goes up, the value increases. So what if I could compound, we compounded hourly, what if I compounded every minute? Or what about every second? Or what about every tenth of a second? What about every hundredth of a second? So the question is, let me come over the top and write this down. Here's my question. What happens to this function? We had something kind of like this, 1 plus 1 over m to the m power, right? Where here what I'm doing is I'm letting r over n, or m equal n over r. And so here we end up with this expression after 1 year. What happens to this as m goes infinity? So as the number of compounds goes to infinity, what happens? We're looking at the right behavior. What's the right behavior of this graph? What happens is that 1 plus 1 over m raised to the m power approximates this number e as m goes infinity. And this value e, you've seen it in a calculator, is about 2.718 dot dot dot. Okay, it's an irrational number. And where does this come from? It comes from this expression, which is directly related to compound interest. Okay, and so here you can have something called compounded continuously. And what compounded continuously is we're compounding constantly, every tenth of a microsecond and more. And you end up with this formula. A of t equals p e to the rt power. And that comes directly from this relationship. Okay? And now, accounts don't really compound continuously, but what they do is they use this information to figure out what the maximum investment you could ever get is, because you can't do better than always compounding. All right. I hope this makes sense, guys. What I want you to get out of this is finding exponential growth, decay, and then understanding compound interest. I think that's very useful. Now, this E thing does show up in a lot of natural contexts because of this funny relationship. This 1 plus 1 over m to the m doesn't just relate to finances, even though that's how we introduced it. It's related to a lot of things. So I mentioned differential equations. E shows up in a lot of places. And what happens, the reason E shows up is because the rate of change on this exponential is always going to be E. It's a weird thing. Okay. If you have any questions on this, let me know. I'd be glad to help you. I want you to do well. And I hope you have a great day and a great week. We'll see you later, guys.